Okay, a very warm welcome from my side. I'm Essing from the Technical University of Munich, and today I would like to introduce to you the topic that is about the evaluation of the electrode design of an integrated bionic microflapper for improved fluid flow. Okay, what is this all about? Let's see. So the objective, what we had on this research topic was to take what is already there in nature, and that is the movement of a fish, and use that as a technical implementation. So in the next couple of minutes we are going to learn about how fish swim and how we can use that to imitate that fish's movement on a micro level. And to do that, we first of all are going to talk about the idea. So, like, what inspired the design and how did we implement that? How we design the electrodes for our microflapper that is imitating the fish's movement. Thirdly, we are talking about the necessary electromechanical simulations to predict the outcome of the flapper's movement. Second least point will be the difference between our measurements and our experiments, and why the reasons, what the reasons might be for that difference. And finally, we're going to wrap that thing up and see how that worked out. So let's just dive into it. We have that fish moving. So first of all, the thing moving here on that presentation up there is just the so-called undulation movement. What is undulation movement? Well, it is basically just a movement of a bending line where each element next to each other has a slightly phase shift to the adjacent one. So in this case, you can see that. Let me grab the laser pointer here. You can see where this whole thing is moving. The phase is moving at a different point in time through the zero line of this bending line, right? So basically the amplitude is increasing with the flapper length, while the phase is changing with the wafer length. And you see that already. This already looks like a fish that is moving. So I made a small drawing of a fish here that is moving its tail back and forth. And by doing that, creating vortices that are going in the direction behind the fish. So with that, the fish transfers momentum into the fluid and vice versa, and the fish moves forward, while the vortices move backwards. And our idea here now was to just basically hold the fish's head and let the fin flap around to move the fluid. Of course, we cannot do that to fish, so we came up with a design for a micro level flapper. But the takeaway from this slide here is that we have a thing like undulation in nature, and that is nature's principle to transfer momentum from a solid into a fluid, and we would like to use that to move on a microscale fluid, for instance in the microchannel. Might be of use for lab-on-a-chip applications, even for micro swimmers, so basically just mimicking a total fish on small scale, but that's far away. That is a pie in the sky. We're just talking right now about how we can at least mimic that movement on a micro scale, so a very beginning on that matter. Another interesting thing is here that actually the vortices have the reverse direction compared to the common wave. You know the common wave where we have an obstacle in a fluid flow and vortices will be created behind that obstacle. But in that case, the vortices will have the reverse direction, like the reverse orientation, which leads to a jet flow in the direction of the object behind the stream. In our case, it's totally different. We have the inverse phenomena where the vortice is here. You see that in the inner part between those two up and lower vortices, a stream will be going in this direction, from left to right, and this is our aim to move fluid. So how did we transfer that into a technical application? So you see on the right hand side basically how we build up that structure. So it's already in this figure, the flapper is already inside a microchannel, and the interesting thing here is now you can already see basically the form of the fish, the blue line, and if we zoom in a bit we can see the sandwich structure that we used to create that undulating movement. And we use aluminum for the electrodes, aluminum nitride as the piezoelectric functional layer that is using the D3-1 effect by applying a voltage between the aluminum electrodes and the molybdenum electrodes below that aluminum nitride. We create through the D3-1 effect a bending that is basically doing something like this, and since we're doing that on both electrodes with a phase shifted signal, we can kind of approximate this undulating movement, and you see that in the red line here. So this is the theoretically possible bending line for an imitation of undulation movement with just two electrodes. Of course, I agree it's not as beautiful as the blue line, which would be the perfect undulation with a phase shift between each element. But since we just have two electrodes on this design, we can basically reach theoretically the red line's bending curve. But you still see that there is an undulation happening here because we have this phase shift when the flapper goes through the zero line here. Okay, so yeah, and our focus here was to figure out what electrode design might be the best case. So we have segmented electrodes that you see here, but we could change the form and the geometry of the flapper and see what happens to the undulation movement in that case. So what you see on the right hand side here is the different electrodes design we have. So we have a variation of electrode designs varying in length, width, form and covered area. With covered area, of course, we mean we're talking about the area that the electrode is covering off the set flapper. And basically I will just go briefly through the different electrodes designs here. So this scale here is the real scale for every flapper here. So the length of flapper C, for instance, is 1000 micrometers, which is of course 1 millimeter. So that is the dimension we're talking about here. And we just go briefly through that. So the difference between A and B is that A is just wider as B, everything else is kept the same. C is of course longer, but still smaller than D, and F is smaller than C. So we started at F, the F length, double the length for C, or triple the length for D. The rest is kept the same. And then we have a different set of electrode designs for G and H that vary completely from the other forms, because in that case we don't have a totally covered area for the electrodes, but a very specific other design. For instance, with G we have segmented electrodes. We changed the form in a way that we decoupled the left and the right side of the flapper. And what is also very important here, the aluminum nitride layer is only under the electrodes for the flapper G and H. So we have a very high decrease in the covered area of aluminum nitride, which is, as we know, a rather stiff material. So this was also to see how we can reduce the stress inside the layers of the flapper. So this is what we did with G and H, meandering structure for the electrodes, and also underneath the electrodes a meandering structure of the aluminum nitride to decrease the stress inside the layers. Okay, and you might ask, what is the difference between B and E? But some of us with the great eyes see that there is some small black line between B and E. The rest is kept the same. And this small line between the top electrodes of E, the distal and the proximal and the distal electrodes, is a small notch that we put inside the aluminum nitride to decrease the total stiffness of the structure, so that we can actually, the hope was, or the aim was, that we decrease the stiffness of the total structure by applying this small notch between the top electrodes. Okay, so this is about the different electrode designs we tested for the flapper. So let me just briefly go into the simulations we applied for those, and this is a small sketch we have on the right side here. So this is our just an example from our finite element simulation we applied on those flappers. What we did was we built a model that is piezoelectric and mechanically coupled for each flapper variant, but we did not include complete bidirectional simulation for the interaction between the flapper itself and the fluid around it. We approximated this behavior by applying a damping force that is depending on the velocity of the flapper. So the higher the velocity of the flapper, the higher the damping force against the flapper would be, to approximate the behavior of the fluid. In that case, we did not calculate the vortices that we will introduce into the fluid by moving the flapper. That is another topic we cannot tackle today. And our results here already, you can already see, first of all, in this picture here, we have this, this black line that is the initial position of the flapper, and if we then apply the voltage between the on the different electrodes, we then see that the flapper would be moving, and you can already see in the results of the simulation that at this very point here, which is the symmetry plane at y equals 0, we can see that the deflection already is moving in undulating manner. So this is just a small dive into our simulations. So we did finite element simulation just on piezoelectric and mechanical structures, no fluid at all. Fluid is approximated with a damping force depending on the velocity of the flapper working against the movement direction of the flapper. So high velocity, of course, high damping force, which would happen in the fluid as well. So how did we approach the measurements here? So the question you might ask is like, what is the optimal actuation frequency for the flapper? Because ideally, of course, the higher the actuation frequency, the more fluid we would move, you might guess. Unfortunately, this is not the case, because the closer we get to the eigenfrequency, the first eigenfrequency of the specific flapper, the less undulation we get. Because in the end, when we reach the point of the eigenfrequency, the flapper will just be moving in the first eigenmode, which is just a resonant movement of the flapper, and there is no undulation at all. So what we did here was to figure out what might be the sweet spot for our actuation frequency, and we figured that like 1/10 of the first eigenfrequency is at least far enough away to not get into a resonant mode, but still too far away to get a decent deflection. So what we did was just actuate with half of the first eigenfrequency as a compromise to get, in that case, the trade-off between no undulation but high deflection and undulation with sufficient deflection. And to do that, we excite the top electrodes with a sinusoidal voltage signal that has a 90-degree phase shift between the two electrodes. And we applied 50-volt peak amplitude for the distal electrode and either 25-volt or 10-volt peak amplitude for the proximal electrode. You will see why we did that in the next slide. And here we see, we figured by the simulation that we get approximately the best undulation for a ratio of the distal voltage peak against the proximal voltage peak of 5. And since we wanted the highest voltage to get the highest deflection, of course, we had as a limit 50 volts, so we applied that on the distal electrode and then a tenth of it on the proximal electrode. On the other hand, we had, as a comparison, we had 25 volt as well. So first of all, the ratio of 5, and secondly, a ratio of 2. So we see in the results here that the tip displacement is indeed higher for the ratio of 2, but the undulation is not. So in that case, of course, if we apply a higher voltage on the proximal electrode will bend more, and thus inducing a higher tip displacement in the end of the electrode. But we figured that the undulation is worse in this scenario. So now a small slide about the measurement versus simulations, where we see that we have the predicted displacement quite well for highly elongated flappers. For case D, for instance, that would be that one here, highest spatial length, but unfortunately we did not match it perfectly, but it's just an error of deviation of 5%, so this is okay so far. But for case A, on the other hand, which is a very small flapper, we get an error of 280 something percent. See, the measurement and simulation results are varying severely. Our explanation for that might be that we don't have a complete bidirectional coupled fluid structure interaction, and our approximation with the velocity depending damping force comes here to a limit. So this might be an explanation for that this approximation works better for large flappers for that case. Okay, so our conclusion on that is that the most promising designs exhibit a high distal flapper length and flat electrodes, which was design D. Unfortunately, on that case, we have a limit in robustness, right? Because the longer the flapper gets, the less robust it will be in the case that it's moving fast or it's subject to vibration. So, but on the other hand, we have estimated and optimized the available and calibrated models, so we can work deeper on that to get a more decent understanding about how we have to develop the models for our flappers. And our models can be a guidance for optimizing either the geometry, the electrode design, and even the actuation pattern. So we can even, we are convinced that we can even improve the actuation pattern, so regarding the phase shift and the voltage. And our next step here is we definitely need further investigation of the fluidical mechanical coupling, so that bidirectional coupling between the fluid and the mechanic part, to get a more deeper understanding about the small flappers. And we think that this way we can just easily do more precise simulation on that. And what also would be a next step would be the investigation of flappers that have a higher number of electrodes, because our assumption here is that we can then mimic more closely the undulating movement, because the more electrodes we have, the better the undulating movement will become. At least that is our hope. Okay, so for now I'm looking forward to your questions, and see you in the meeting room here. Thank you very much.